sub, you may replace object A with object B at any time if A equals B. So what I've got shown here are the various number conversions that we usually do. We can start with a fraction. We can then slowly pull it apart. 8/3 is the same as 6/3 plus 2/3, which is the same as 2. 6/3 is 2 plus 2/3. And then we can shorten it. And here's another exception, and honestly, I don't like this one, but again, we're stuck with the notation. Technically, that should be 2 times 2/3, and if you don't write the 2 big enough to make it look like a whole number versus a fraction, yeah, I know. How much is big enough, and do kids always get that the first time around? Usually not. But 2 and 2/3, that's not 2 times 2/3. It's a mixed number. Living with that, 2 and 2/3 is the same as 2.67, and of course we've rounded this off. So you could technically argue 2.67 is not exactly 2 and 2/3, but we accept that because usually the book will tell you round off to the nearest tenth, the hundredth, the thousandth, whatever. And then that becomes accepted as exact, and it becomes accepted as equal. And 2.67 is the same as 267%. So now I can take 267% and I could put it in the place of 8/3. Whatever the problem may be, I can swap any of these. I can take 6 and 2/3 out. I calculate, figure it out. Oh, and then I can put 2 and 2/3 in its place. That's substitution, because object A over here equals object B over here. So I can take A out and I can put B in, and the problem still works because the value never changed. Only the look. So we're fine. Coming down here, we have 7/5, which is the same as 5/5 plus 2/5, which is the same as 1 and 2/5. And here we go with our mixed number, meaning 1 and 2/5, not 1 times 2/5. And that equals 1.4, which is 140%. So again, we can swap whatever, wherever, because the value hasn't changed. The looks have. It's more convenient, if perhaps I'm in the stock market, and I think they will often use mixed numbers there for their stocks. Algebra books tend to like a fraction and not change to a mixed number. If we're dealing with retail and prices, we'll use decimals or percents. If there's a price increase or decrease, we tend to use percentages. So, it's all the same value straight across. The look just fits different markets, different purposes, different types of problems and solutions. So we take one out, put the other one in, fine. The value never changed. You can substitute. Another very practical application of substitution is in formulas. Instead of writing out the calculations needed for a circle with a radius of 1, and then another one with a radius of 2, and then another one with a radius of 3, we just make a generalized pattern or formula for it. And now you just remember one formula, pi r squared, and then plug in whatever radius happens to be there for that circle. And you'll follow the same steps. So it's like a template. And so we get pi. Again, we take the pi out and we substitute it with 3.14. Maybe a book will want you to use it out to the thousands, 3.14159. If I'm remembering right, and the 5, 9 would round up to a 6, whatever they'll have you do, or you just do it on a calculator without any rounding at all, and it may take it out to 8 or 10 places, whatever the calculator does. And then we times it by 7.4 squared. And now we go through the same order of operations. I will do my power, my function first. Then I will multiply, and then that's it. So there's my answer. After you have done the substitution right here, then it's just down to calculate, and you go over in, fun, mud, colt, and you proceed as normal. Again, we can take the volume. I think this is the volume of a pyramid. 1/3 times length times width times height. So I may look at a diagram, or the book may just give me a list like I'm doing here. The length is 5, the width is 7, the height is 11. And I will take the L out, and I will put the 5 in its place because L equals 5. A equals B, A comes out, B goes in, the game goes on, just like substituting football players in a game. We figure they're equal. Hey, this is a quarterback, he's a quarterback. I can take this quarterback out and put that other quarterback in, and he does the same job. So 1/3 times 5 times 7 times 11, order of operations, in, fun, mud, colt. And then do they want the answer in fractions? Because my usual rule of thumb, if there's no particular instructions, if the problem starts with fractions, I tell the students then end it with a fraction. If the problem starts with decimals, then give me an answer with decimals. Usually there's an instruction, but not always. Now, one more, and I want to cover a common mistake, and this has, again, to do with a notation. What is 4x squared y when x equals -2 and y equals 3? So notice that x equals -2. X doesn't just equal 2. There's always a sign, just the same way y equals a +3. Now, there's no trick there, but just pointing that out, that it's a -2, because now we have 4x squared. Well, x squared means x times x. And all of the x is -2. Notice the parentheses that I'm drawing here, and notice that I've got parentheses squared. Because the problem here is 4 times x squared, 4 times x, and x is all of the -2. So the problem has to have the parentheses. I am going to have 2 negatives here. How does that different when you have a -2 squared, and then that equals negative times 2, like that? How come I only have 1 negative there? Well, here the problem started that way. Here the problem just says x. And so it's all of x times all of x. And that x has a -2 inside of it. Here, this problem is not saying x squared. It's saying -2 squared. It's, again, it's a notation thing. The exponent literally applies to only what it is next to. And here the problem is written differently. It may look the same here, but the implication is different because it is x times x. And that means whatever sign may be with x, it also has to get repeated. So I just always have my students, if they don't literally write it out, I say in your mind, you have to make sure that there are parentheses there so that whatever is getting the exponent applied to, everything inside the parentheses gets the power applied to it. So that's why there are 2 negatives and there are 2 2's. This is getting a bit messy, but hopefully you see what I mean. And there are implied parentheses here because we have to have an x times x. If we didn't have the parentheses, then I only have one negative, then it's like a -2 times a +2. That's not x times x. I have now changed my x. One of the x's is -2, the other x is a +2. No, it's x, which is -2, times x, which is -2. And that's how we get 2 negatives in this case, because there's another one in there. Yeah, that's not going to show up. Let's maybe let's draw it this way. So now I get a -2 times a -2, whereas this is negative times 2 times 2. There's a difference there. Be careful. Just put your variables, when they have powers, put them in invisible or visible parentheses, and then that way nothing gets left behind and everything is multiplied, divided, multiplied usually the way it ought to be.